Welcome back to Software Design and Architecture, Part 2, Design Patterns. In this lecture, we are going to focus on Creational Design Pattern. But before that, let us revise what the definition of design pattern is. What is a design pattern? Pattern is a description of solution for recurring problems in software system design, which is dealing with microarchitecture. The list here shows the classic design pattern according to the cataloging done by the Gang of Four. These patterns are generally categorized into three: creational, structural, and behavioral, depending on their purpose. This is not an exhaustive list. There are new patterns created from time to time. In today's lecture, we'll be looking at singleton, factory method, and abstract factory examples. Creational design pattern is a pattern that deals with object creation mechanisms so that the objects are created in a manner that is suitable to the situation. The three examples are singleton, which ensures only one object created; factory method, which defers instantiation of an object to one of the subclass during runtime; and abstract factory, which is similar to factory method but returns the object from multiple choices. Let us look at the first design pattern, singleton. Singleton's intent is to ensure a class would only have one instance, and that one instance has a global point of access to it. To achieve this intent, the structure of the class must follow this guideline. The name of the class, it must contain a static field already assigned with a single object. The constructor must be private. Since the constructor is private, the only way to get the instance is to have a static method called getInstance, which would return the unique instance as referenced by the static field. We can have other data and other operations, depending on the purpose of the class. But to achieve the intent of being a singleton, that means only one object per class for the system, these are the structure guideline that one must follow in a design. Let us look at one example. You have probably heard of java.util calendar, which provides calendar object to Java programs. The calendar object will return the system's date, which include year, month, day, and even the time. There's one method called getInstance in the calendar class. GetInstance will return the concrete implementation of the calendar class each time. Therefore, calendar cannot be a singleton, because by calling the getInstance method, each time we will return a new object. Let us look at the following example. It shows the main method, which has declared two calendar variables, C1 and C2. In the following lines, calendar getInstance will return new object to C1 and C2. In this example, we have two objects. These two objects are different. We can test them by having the first object in C1 added with one month, whereas we ignore C2. So when we print out the date of C1 and C2, C1 would be 1 month in advance of C2. This shows that C1 object and C2 object are different objects. There are scenarios whereby we want to have a global calendar. For example, in a system where the tasks need to be coordinated by time, the synchronization is important. Thus, we need to make sure that there's only one clock for the whole of the system. We can make use of calendar, but calendar is not a singleton. So it is not impossible to accidentally create more than one calendar object. This is not preferred. Therefore, we should implement singleton. We shouldn't modify calendar class. Remember solid design principle, whereby we should not modify classes, we should extend them. So in this example, we have imported the calendar class. We have two classes, My System Clock and Application Class. My System Clock is a singleton. It is a singleton not because of its name, but the way we design the content of the class. Application Class is a user class, whereby it will be creating calendar objects by using both System Clock and calendar. Now, let us see why My System Clock is a singleton. Number one, it has a unique field which has only one object. In this example, it is calendar object. It has a private constructor. It has a getInstance method, which is static and must be returning the unique field. So tell me, is it possible for the user inside application to create more than one My System Clock object? No, not possible. Every time you call My System Clock, it will return only one calendar object, the same calendar object. Even you call it multiple times, it will still be the same calendar object. Let's look at the example here. When we call My System Clock.getInstance, it will return this only calendar object in My System Clock. When you call for the second time, again, it will be calling back the same object, not giving a new one. So how many objects we have? How many calendar objects we have here? Only one, which is referenced by both C1 and C2 variables. Therefore, when I add 1 month to C1, is also equivalent to adding to C2, because after all, both of them are referring to the same object. When we print out C1 and C2, both of them would have the same date. Another creational design pattern is factory method. Consider the following. For an online game, an avatar is a digital representation of the human player. At design time, the system will not know the gender of the avatar chosen by a player. The avatar can be determined only when a player registers during runtime, either a male or a female avatar. Propose a suitable design that will allow above creational intent to be achieved. The solution will be to use factory method creational pattern. In this design pattern, one first creates interface for the avatar. Then create subclasses, male avatar and subclass female avatar, that implements the interface. Note that both would inherit the same method to override the interface method. The other class, which is avatar factory, will contain the factory method, which is the underlying create avatar tries string avatar. This factory method will return the subclass concrete objects not the interface. This is shown in the following code, showing the factory method create avatar. Depending on the user choice, male or female, it will return the corresponding concrete class objects. Let's look at example 2 of factory method. Recall that Java Utility Calendar's getInstance method is a factory method. Factory method getInstance is needed for calendar because calendar is an abstract. The getInstance method will return the concrete implementation of the calendar class. As you can see here, the class calendar is abstract. And here is the code to get the concrete implementation of the calendar to be assigned to calendar variable. Now, why is factory method needed here? The answer is because the object can only be determined during runtime. That is, when the user enters the time zone, whether in Malaysia or in Europe. The object that is compatible with the time zone will be returned based on the input parameters here. This is the reason why the object should only be determined during the runtime. Now, try thinking in pair. Solution using factory method. Consider this. An Office application allows user to create document to write his or her content. The application can produce a variety of document types, Word document, spreadsheet, or presentation slides, depending on the user's choice. How do we make use of factory method to design this solution? Propose a class diagram. Pause this YouTube and try to figure out the answer. Let's look at another creational design pattern, abstract factory. Abstract factory is not the same as factory method, although both sounds more or less. Abstract factory is a creational design pattern that lets you produce families of related objects without specifying their concrete classes. For example, how do we write a single user interface and then make it portable across the different operating systems, Windows Manager? For example, we want to create a graphical user interface for a system that can be used on Macintosh, Unix, as well as Windows operating systems. The solution is to implement a user interface toolkit that supports multiple look and feel standards for all the operating systems. The benefit of doing so is that the client code now needs to deal with the abstract class only, which is simpler. The client does not need to be aware of the various underlying concrete classes. In this case, the abstract class would be the abstract factory, and then the underlying concrete classes will be the different factories for the different operating systems. In the case that a new factories are added, they'll be added as an underlying concrete class, which does not affect interaction between the client and the abstract class. Let us look at the code for this example. This code is in the client. In the client class, we will declare abstract factory. According to dependency inversion principle, we would prefer dealing with abstraction rather than concrete implementation. That is why we choose to use abstract factory here. Remember, our problem is to have a graphical user interface that can cater a range of operating systems. So this Java code will retrieve the OS type that the application is running on. So using this information, the code will assign the corresponding factory to the abstract factory. In case that it is a Macintosh computer, the Mac factory concrete implementation will be assigned to the abstract factory. If the application is running on a Unix operating system, then it will assign Unix factory to the abstract factory. If it is a Windows machine, then it will assign Windows factory to the abstract factory. Then only the graphical user interface widgets such as buttons, sliding bar, tables, text fields, these are the products. Then only these products will be generated by the factory. If it is a Windows factory, it will generate Windows widgets. If it is a Unix factory, it will generate Unix widgets. And if it is a Macintosh factory, it will generate Macintosh widgets. Note that in this part of the code, we are only referring to the abstract factory, not the concrete factory. So regardless of how many concrete factories we have here, the code here does not need to be altered. This extends the reusability of this code. I'm sure at this point, some of you are not able to distinguish between abstract factory and factory method yet. Doesn't matter. Let's look at this example too, which will help us to distinguish the two. We have a class named SumApp that depends on the interface shape. Shape uses instances of shape solely through the shape interface. So these are the subclasses. The problem is, SumApp also creates instances of square and circle and thus has to depend on the concrete classes. Now, if we have shape factory, SumApp will only need to deal with shape factory to retrieve the products, which in this case, shape, the product of the factory. Now, note that without abstract factory, SumApp will interact directly with the shape interface. With abstract factory, SumApp will interact directly with shape factory to retrieve the corresponding squares and circles through the factory. And this is the code that shows the difference between implementation using abstract factory and implementation without abstract factory. In abstract factory, we will use the abstract factory variable later on to assign with the corresponding concrete class and to use that class to retrieve the products. In this case, square or circle to be assigned app. Now, if you look at the code without abstract factory, the code will need to retrieve the concrete subclasses, which is then assigned to the interface shape. Comparing these two, which one has more advantages? In case that in the future we want to have more shapes. Think about it. Before I end the second part of this lecture, try the following question. Discuss how to write a single control system that is independent from the manufacturer using abstract factory. Good luck!